Hello friends, welcome to Comvolution, enriching minds many at a time. Today's topic is pump sizing. Some people call it pump hydraulics as well. We are not going to take this topic as a traditional one. We are going to have a case study wherein we will understand how a pump is sized in the real world. Let's get started. So this is a design problem which I have created for this case study. Uh, I would suggest you to draw this diagram on a piece of paper so that you can refer to it at a later stage in video. You can pause this video and draw this diagram. I promise you that this will be really helpful for you to understand this video in its entirety. So what uh, does this diagram tell us? So we have a tank which is located at a lower elevation compared to a pump. So this is a suction lift scenario. Uh, if it was located somewhere here at a level above the high point of the pump, it would have been a flooded suction, but this is not a flooded suction. This is a suction lift scenario. This pump is expected to deliver a flow rate of 15 meter cube hour at this point, which is located at 15 meter in elevation from the high point of the pump. You can consider this 15 meter from this point up to the high point of the pump. This 3 meters is basically your suction lift, and this 2 meter is additional length of pipe which is connected in the suction of the pump. This is a discharge pipe of 5 meter. You have a control valve, you have a single bend in the suction line, and you have two bends in the discharge line. All the bends are 90-degree bends. This information is critical in calculating the pressure drop, which we will see in the later part of the video. So let us go step by step. So step 1 is data collection. So what is our required flow? 15 meter cube per hour and a differential head of 18 meters. Now where this 18 meter come from? 3 plus 15. So let's go back to the diagram. So what is basically a differential head? It is the distance between the two liquid surfaces. So the liquid surface in the suction which is filled in this and this point of delivery. So why we have considered this 3 meter? Because we should be able to pump the liquid out from this tank even when the liquid is filled at a point where the dip pipe is touching the bottommost part of the tank. So this height needs to be considered because the liquid would have to be pumped from this point up to this point. Many people do this mistake that they miss this head, and they only consider the discharge pipe elevation, and then later on they face problems. So the total discharge head which is required in this case is this 3 meter, because we have to empty this tank also, and the 15 meter uh, elevation of the discharge point or point of discharge. So step 2 is preliminary line sizing. In suction we are considering the velocity of 1 meter per second. This is important to know few rule of thumbs or good engineering practices. This is one of them. Why do we consider a lower velocity in suction of the pump? Because we need lower pressure drop on the suction side so that the pump do not cavitate. So this is one of the assumption that we can have a velocity around 1 meter per second in the suction of the piping. Then we have to calculate the line size required with this velocity and this much flow. So we apply continuity equation, which is Q equal to A into V, where is Q is flow rate, which is 15 meter cube per hour. A is cross section area of the piping, and V is velocity. So cross section area of piping is basically Q divided by your velocity, volumetric flow rate divided by velocity. So why this 3600 is appearing here? We are converting this meter cube per hour to meter cube per second for unit conversion, because this is in meter per second. So 15 divided by 3600 is our flow rate divided by this velocity, which gives a cross section area of piping as 0.0041 meter square. Now you will have to calculate diameter of pipe, for which the area is equal to this much. So what you will do, you will equate area with pi by 4 d square. So area, which is this value, is equal to pi by 4 d square, and you will get a value of diameter of 0.07 meter or 70 mm. As the calculations in meter, you will get an answer as 0.07 plus some digits. I have neglected them for ease of calculation here. So this will be 70 mm. Now commercially commonly available next pipeline is pipe size is 80 mm. So we can install 80 mm piping in the suction of the pump. So this piping will be of 80 mm, right? Okay, let's go ahead. Then next step is same what we did with the suction side, we will do with the discharge side. Now with the higher velocity, because we can allow some pressure drop in the discharge piping as it is not going to cause any problems for NPSH. And this should not be very high. So this value of around 2 to 3 is a reasonable value. We have taken an average of 2.5 meter per second. So discharge line size is again we will apply continuity equation. This is Q, our flow rate in meter per second divided by this velocity. We got a cross section area, and now we will equate this cross section area, and we will find out diameter of the pipe. So pi by 4 d square is the equation for calculating the area. We will equate this pi by 4 d square with this value, and we will find the diameter, which will come out as 0.046 meter. Next available size commercially available will be 50 millimeter, so around 2 inch. So we will have a discharge piping of 2 inch. So now we know that we have a suction piping of 3 inch and a discharge piping of 2 inch based on the preliminary calculations. Now we will find out pressure drop due to friction on suction side and discharge side. This is step 4. It is one of the biggest step in this calculation. So you'll have to pay a lot of attention from here onwards so that you don't miss anything. So how we will calculate suction side pressure drop? We will use equation for calculation of pressure drop, that is Darcy-Weisbach equation, which is dH, that is head loss in meters, equal to FLV square upon 2GD. So what is F here? F is Darcy's friction factor. L is length of piping. As we are considering it for the suction side, the length of piping will be 5 meters, which is suction pipe length. If when we will be considering for the discharge side, we will be considering all 15 meters, right? So then V. Now what is the velocity on the suction side? We have considered 1 meter per second, but later on we selected a higher commercially available pipe size. So if you back calculate with that cross section area for 15 meter cube per hour, you will get a suction velocity of 0.829 meter per second. Similarly, we have considered 2.5 meter per second as a preliminary velocity, and then we calculated area for the cross section, and with higher size, if you back calculate the velocity, it will come out to be 2.12 meter per second. So here you don't have to do anything, you just have to back calculate velocity from the selected diameter, which is 50 mm and 80 mm, and you know the flow of 15 meter cube per hour. So these are your velocities. So putting those values in this equation, only remaining factor is Fd, which is Darcy's friction factor. Other all the values are known to us, only this friction factor is to be calculated. Now how do we calculate friction factor? To calculate that, we first have to determine whether the flow is laminar or turbulent. Now this is taking us to fluid mechanics or fluid flow calculations, maybe from the second year in chemical engineering, wherein we will find out Reynolds number, which is du rho by mu, wherein d is pipe diameter, u or v is velocity, rho is density, and mu is dynamic viscosity. So viscosity of water at room temperature is this much Pascal second. Outer diameter, it is for the suction piping, if you remember. So this is 80 meter, 0.08 meter. velocity after calculation is 0.8293 meter per second, and density is 1000 kg per meter cube. So if you put all this value in this calculation, in this equation, you will find out Reynolds number is 78,000. Now if the Reynolds number is higher than 2100, then the flow is in uh, trans, uh, say transition or transitional flow, and even higher is then turbulent flow. Comment in please comment the value above which the flow becomes turbulent, but for this Reynolds number it becomes a turbulent flow. So why this is important, why Reynolds number is important, and why this determination of turbulent and laminar is important? Because we have two equations. If the flow is laminar, we have a very easy calculation for a Darcy friction factor, which is 60 power upon Reynolds number. But in our case, we have found out that our flow is turbulent, so our friction factor will have to be calculated by this equation. Now this equation, though it looks really tough, we can solve it by putting in some efforts, but there is a shortcut. You can refer Moody's diagram and find out the friction factor. This is the Moody's diagram. So for this, we actually need to know the relative roughness. What is relative roughness? Epsilon by d. So this is epsilon, which is roughness in millimeters, and d is the pipe diameter. So if you see, uh, for commercial steel pipe, epsilon is 0.045 millimeter, and our pipe size is 50. So epsilon by d is around 0.009 meter. Okay. This is for the suction side, and 0.00056 for the discharge side, because discharge side is higher in diameter. So these are the relative roughness which are there for our suction and discharge piping. I hope you get the point, because in Moody's diagram you need to plot this epsilon by d, which is relative roughness. Okay, you can see this here. You have relative roughness, and if you have to track the curve all the way around where till you coincide with the Reynolds number, and then you can find out the friction factor, which is plotted over here. Okay, so these curves are each uh, for each relative roughness number. So if you check for 0.0009, this is somewhere here. 001 is really close to 0009. You have to track this line, and you have to check where it coincides with our Reynolds number of 78,033. So when you plot this, it is coming somewhere around here. You can find that a friction factor is 0.025. So 0.02 is here. So somewhere here it coincides the two lines with each other. So we get the value of F from Moody's diagram, which is 0.025. Okay, now we have all the values, so we can find out suction side pressure drop. So suction side pressure drop, after putting all those value including F, which we recently calculated from the Moody's diagram, we get a head loss of 0.087 meter. Okay, so next step is discharge side pressure drop. Now I have taken a shortcut here. We will have to find Darcy's friction factor in the way which we found out for the suction side. You will have to find it for the discharge side also. I have considered the same friction factor for ease of calculation and shortening this video to some extent. So by putting the all other values, only one value will change, wherein the discharge velocity is 2.12 meter per second, and the length of pipe will be considered as a 15 meters, because it's a discharge piping, so it is higher in length. So for this case, on the discharge side of the pump, you can calculate the head loss using the same equations and the same variables, and you will get a discharge head loss of 1.71 meter. Okay, so you got a suction head loss of 0.087 meter, you got a discharge side pressure drop of 1.71 meter. What's remaining? The pressure drop due to fittings. So pressure drop due to fittings can be calculated as K into V square divided by 2G. So what is K? K is a manufacturer published factor for each fitting. V is velocity and G is acceleration due to gravity. Now this table you can see for each fitting like gate wall, 90-degree elbow, angle wall, diaphragm wall, based on its opening percentage or opening portion, you get a K coefficient. For our case, we have a one elbow of 90-degree in suction side, two elbows of 90-degree in the discharge, and one control globe wall in the discharge piping. If you have drawn the diagram, you would be really able to see all these things in the diagram. That's why I told you to draw the diagram before starting of the video. You can even still now pause it, go back, check that diagram, draw it roughly on a paper. You will be easily identifying all these things. So K value for 90-degree bend is 0.75 and K value for globe wall is 9. So where is globe wall? Here. So open globe wall we have considered it as 9. This is for a simplification purpose. We can consider it as partially open or based on process conditions. If it is kind of a globe wall with a control loop, then it can remain partially closed also. So but for simplification, we have considered it as full open, and the K value for elbow is 0.75 as you can see here. Okay, so the calculation for suction side elbow K 0.75, velocity on the suction side. This you will have to take care that you take proper velocity. This is the elbow on suction side, so this is the velocity for suction side squared divided by 2 into acceleration due to gravity. This is head loss due to suction side elbow. For discharge side elbow, you have two elbows in the discharge piping. You will consider 0.75. Now this is velocity is 2.12 because it is a discharge side velocity squared. So this velocity is squared divided by 2 into acceleration due to gravity. This comes out to be 0.343 meter. For control wall, K value is 9. Velocity as it is in discharge piping, discharge side velocity squared divided by 2 into gravity 4.12. So if you add all this, you get a total loss due to fittings. So now we have a pressure loss due to suction piping, pressure drop due to discharge piping, and pressure drop due to fittings. So we can calculate total head loss, which is 0.087, which is for head loss in suction piping, 1.71 and 4.489, which is for the fittings. So this is the total head loss. It is calculated in meters. So this is meter of water column in our case. Now the head required by the pump, it is suction lift, which we earlier discussed. It is 3 meters. The discharge head where the pump needs to deliver 15 meter plus the total head loss. So summation of this will be the head required by the pump, which is calculated as 24.28, which is approximately equal to 25 meters. So the head required for the pump to do this duty of delivering 15 meter cube per hour flow rate is 25 meter. So we need a pump with a duty point of 15 meter cube per hour and 25 meter head. So we have reached the point wherein we know that the duty point of the pump should be this much. Now we can think of selecting which model is best for this particular set of flow and head. Okay, so next step, selecting the right model. You might have seen pump curves differently because generally it is head versus flow for one single pump. This is basically a family of pumps. Manufacturer give this kind of curves so that you can select appropriate model for your application. So if you can see, on the x-axis you have flows, on the y-axis you have head, which is generally there in normal pump curves or a individual pump curve. Now for our case, we need a pump with 15 meter cube per hour and 25 meter head. So what we will do, we will draw a line from 15 meter cube per hour and 25 meter head. The point of intersection will be our operating point. Now the model in which this intersection point is occurring, this model is best suited for this particular operation or this particular transfer of liquid. If this pump if this point is really close to the line, then existing impeller size or standard impeller size will work. If this point is way below this line, it means you will have to use a trimmed impeller in this case, because you will your operating point is well below the normal pump curve for the standard impeller size or the highest impeller size. But basically you will get this operating point easily in this pump curve. So the number is 65-40315. This is the pump model number which we are going to select. So this is how we select pump models for our given operation. Now next step is NPSH calculation. So for NPSH, what is NPSH? We must have some positive head for the pump so that it does not cavitate. The equation for NPSH available is atmospheric head, atmospheric pressure head plus gauge pressure at the suction point, plus or minus elevation, or you can say it as a suction lift or suction or a suction side head, friction loss, head loss due to friction in meters. Every value in this equation is in meters, minus vapor pressure. So you have to convert this vapor pressure in meters. What is this NPSH-A? So this is basically NPSH available in the system. So we have a pump which is lifting liquid from a underground or say from a lower elevation point to and delivering it to a higher elevation point. So the system needs some the system have some NPSH, which is NPSH available, which we are calculating. Now this NPSH available must be the NPSH required by the pump must be less than this NPSH available. Then only this pump will work without cavitation. We will do the calculation and later on understand the concept with numbers. So putting the values, atmospheric pressure, so you have to convert it to meters of water column, which is 10.33. If you convert 760 mmHg to meter of water column, it is 10.33, plus then this is gauge pressure at the suction point of vessel. So the vessel or the suction is not pressurized, so you can keep this value as 0. It is atmospheric, so there is no additional extra pressure apart from this atmospheric pressure. Now this is static head or static lift. So when it is static head, so the liquid level is available above the eye point of the liquid, then this value is positive. In our case, we have a suction lift, so we have to lift the liquid, this value will be negative. So this is -3, right? Then we have a head loss due to friction in suction pipe, because NPSH is more relevant to suction side of the pump. It only takes the pressure drop of suction piping. So this value, which we have already calculated, we will put it here. And vapor pressure, so vapor pressure of the water at 30 degrees centigrade, it will come in it will be available in millimeter of water column or millimeter of Hg. You will have to convert it to meter of water and put this value here. It will also be negative value. So by doing this calculation using this equation, you will get a NPSH available as 6.478 meter. Now we need a pump for which NPSH required is less than this value, then only we can use that pump. I hope you got the point. So to prevent the pump from cavitation, we need a pump whose NPSH is less than 6.478 meter. I do not have NPSH curve for the pump which we selected over here. So just to demonstrate you how to check NPSH, uh, this kind of pump curves are there. You have a NPSH line over here. So for example, you have a 15-meter cube duty point, then this particular pump, which is not the selected pump by the way, this will need a NPSH of around say 6 or 7 meter. So you have to track this flow value up to the curve and then go on the y-axis and check what is the NPSH required. This curve is available in all the pump manufacturers curves, wherein it gives a detailed curve for one pump. So it is not available with family of pump curves, but when it gives you individual pump model curve, then this value, this NPSH required line is available. You can see the trend that when the flow increases, the NPSH required increases. So from here you'll have to ensure a pump. So this pump in our case, if you see our requirement, we need a NPSH pump with a NPSH requirement less than 6.4. This is really a cut to cut. It is around around 6 or something. So we will avoid this. We can go with this pump. If you convert this liter per second to meter cube per hour, I guess it is around 4 point some value, and NPSH required here is this is the meter line, right? So it is always less than 2. So this pump needs NPSH less than 2. We have NPSH of around 6.4, so we can use this pump without cavitating it. So this is about selection of pumps for a particular application. I hope you like the video. To know more on pumps or any other equipments, do comment in the comment section. Like, share and subscribe. Thank you.